So in my last video, I said that most of my next videos will be related to this statement right here. That pretty much means I'm going to be doing a mathematical logic course here. Not exactly. I'll be showing you how to write proofs. Okay, so firstly, this question might seem trivial, but you're going to hear the word trivial a lot when doing proofs, by the way, so just keep that in mind. What is a proof? So a proof is a mathematical statement that is derived from axioms. Sort of. But basically it's where you prove something mathematically. So I'm going to start off with a very simple proof. Okay? I'm going to be proving that 1 plus 1 equals 2. The Principia Mathematica has a proof like this. It's quite long though, so I'm going to give you a very simplified one. So no, I shouldn't write it like that. The successor of x will equal x plus 1. Actually, I probably shouldn't use that notation. So the successor of x is the number that comes after it. So let's do this. So 1 plus 1 equals 2. So what is the number that comes before 1? It's obviously 0. So 1 plus the successor of 0 equals 2. And the definition of addition says that we can move this term inside. So it's going to be the successor of 1 plus 0. And the Peano axioms say that we can cancel this out. So it's going to be the successor of 1, which is 2. So 2 equals 2. This proof might not actually be a very good example, so I'm going to give you a better one. We're going to be proving the product of prove that the product of two even numbers will be an even number. And basically, I'm going to say prove that 2k times 2n will equal 2m. Because basically, an even number is any number. I should probably write this down. Okay, basically, an even number is any number that is any number that is an integer multiple of 2. So basically, what I'm going to do here is I'm going to write it out. 2k 2n. Here, since multiplication is what's the term? This multiplication is commutative, we can turn this into 2 times k times n. And here we can multiply this, so 4 times k times n. Okay? And I think I should, alright, so anyways, this will be the same as 2 times k times n. And this right here, and since remember, the integers are closed under multiplication. Therefore, this itself will be an integer. So therefore, this is going to be 2 times an integer, call it m. And this, by definition, is even. Now, this is what's called a direct proof. You often can't do direct proofs because, for instance, I'm going to ask you to do a direct proof that the square root of 2 is not an element of the rational numbers. This is really hard if we only allow direct proofs. I don't even know the proof. There probably isn't one, honestly. But instead we can resort to other proof techniques. Here we're going to use a proof by contradiction. So mathematical logic states that P implies Q is the same as not P implies not Q. Because if we negate these this, the negations cancel out, so you're going to get P implies Q. But please, quick reminder, P implies Q is not logically equivalent to not P implies not Q. This is the logical fallacy of denying the antecedent, and you might not want to include that in your proofs. However, it is equivalent to not Q implies not P, I think. Like if you have, let me think here. So, all humans, wait. Okay, let's just ignore, I forgot I said anything. That's actually called the contrapositive of the original thing, of the original statement, and there's another technique called proof by contraposition that we're going to get to later that uses that requirement. But anyway, here we're going to get to the proof. The square root of 2 is irrational. The Q. So basically, in order to do a proof by contradiction, we assume that this is true. We assume that this is not true. So assume that the square root of 2 is rational. Okay? Now, this will mean that the square root of 2 is equal to P over Q. Just a quick note, P and Q are natural numbers. So that means they are counting numbers. And now, in order to get rid of the square root, we can obviously square both sides. So 2 equals P squared over 2Q squared, actually. And now, this is going to give us 2Q squared equals P squared. This means that P squared is even. This chalkboard is so tiny, I have to move around all the time so you'll actually be able to see what I'm writing. And this means that P times P is even. Therefore, since the product of two evens is an even, as we just showed, this means that P is even. So I'm going to actually rewrite this whole thing now. So 2Q squared equals P squared. Imply that, in quick note, P is even. Now, what we can do here is since P is even, we can rewrite it in the form that this is going to be equal to 2K, where K is an integer, squared. I'd probably say K is an element of the integers. Now here we can simplify, so 2Q squared equals 4K squared, because you distribute this. And now, this is the point that is quite good, because we can divide both sides by 2, and we're going to get, to get rid of that, 2. So 2K squared. So Q is equal to 2 times K squared. Therefore, as I just showed, since Q is equal to 2 times some integer, I'm going to write this way. P is even, Q is even. So that means we have an even over an even. However, the square root of 2, if we say that it's equal to P over Q, we're assuming that P over Q is an irreducible fraction. I forgot to state that, but that is actually what an assumption you're supposed to make at the beginning. So that means that since P and Q are both, so since P is even and Q is even, that means that P over Q is not irreducible. And this means that the square root of 2 cannot equal P over Q. And this is our proof. This means that the square root of 2 is in fact irrational. So I'm going to write QED, quod erat demonstratum, in a triangle made out of dots. I've proven this. And now, I think you should understand the basics of mathematical proofs. In the next episode, if I make a next episode, we're going to get into proof by induction as well as proof by contraposition. So 2 more advanced proof techniques. The reason I didn't cover proof by contraposition today is not because I don't know how to do it or because I think you should learn it later. It's just because I couldn't think of any examples of famous proofs that used proof by contraposition. Proof by induction, on the other hand, is used very often, and next time I'll use it to prove next time I use it to prove something we used earlier today, that multiplication is commutative. Arrivederci.